Hello, this video is on the first part of the 2011 Oxford PAT. So see if anything has changed in the advice here. We've still got the 2 hours, we've still got no calculators, still got G is 10. Exact answers for part A, 2 significant figures for part B, right? So nothing's changed from the previous year. Let's have a look then. So yeah, maths comes up first. Find the values of theta between 0 and 2 pi which solve this. So we want to, it's hard to change the sine, it's easy to change the cos squared. So let's get a quadratic in sine theta. So minus 2, 1 minus sine squared theta equals minus 1. So we've got sine theta minus 2 plus 2 sine squared theta plus 1 is equal to 0. So 2 sine squared theta plus sine theta minus 1 equals 0. 2 sine theta, that's going to have to be the minus 1, isn't it? And then sine theta plus 1 equals 0. So we've got sine theta equals a half, or sine theta equals minus 1. That would be 3 pi divided by 2 is the only solution we've got in that range. And then this one will be, so theta equals that. Theta equals, so 30 degrees, pi divided by 6, or 5 pi divided by 6. That's a fairly standard question, that one. So a nice 4 marks to get started. Sketch this function. Well, this looks a lot more complicated than the previous one, and we're getting fewer marks for it. Well, it has given a range, right? So I might do this in 2 ways and see which one comes out better. Because you could do, let's put in some values. We know this is just going to be a sine, regular shaped sine function. So we could do that. Let's try the plot in some values. So we're going from 0, actually shifting this up 3 means we're not going to have any negative numbers. So let's draw, I'll leave a little bit of space in case I've got that wrong. So we're going up to 12. So if we were just going to plug in some values, we'd say we've got, when x is 0, we've got sine of, what's that going to be? 0 minus 3 minus pi. Well, that's still 0. So we're going to start at 3. So we know we've got that at 3. Let's go up in, well, if we get to 12, what have we got with 12? We're going to have 9, so a sine of 3 pi. So that's also going to be at 0. All right, so every time x is a multiple of 3, we're going to be going through this 3 because that'll end up being 0. So let's put a 6 there, a 9 there, a 3 there. Which way is it going to go then? So as we move up from 3, this is at minus pi, it's going to be going negative, isn't it? But let's just put a 3 in, I suppose, because you'd get 3. Oh yeah, I just said all of these were 0. So let's try it then. It's going to go down first. It's definitely going down first. Yeah, if you put in x is 1, say, you've got minus 2/3 pi, which is in the negative bit. You know, if you think of your sine function, it's doing that between minus pi and pi. So if you're at minus 2/3 pi, you're in here somewhere. So it's definitely going down. Our minimum that we can get on this is 3 minus 2, which is 1. And the maximum we're going to get is at 5. So that's, we're just going to have a sine wave going between those. So yeah, a bit of wonky in my drawing there, but these are all 5s at the peak. These are 1s at the minimum. And then we got 3s down the middle. So right, so that's certainly one way of doing it that wasn't that painful. We could, if you were feeling adventurous, maybe go into looking at what seems to be 4 transformations of graphs here. So if we rewrote that then to try and make the transformations inside the function a bit easier to see. So we've got x times pi over 3 and then minus pi. So these two are easy. Yeah, so the 2 we're just doubling the height. 3 we're moving it up 3. So that's fine. So what have we got going on here? This is our rescaling of the x-axis. So if we've started with our, we're going to need a little bit from the side as well. So if we started with this, this is just our basic sine function. That's going through minus pi, 0, pi, 2 pi, 3 pi, etc. So we'll leave these two easy ones for the end. Let's deal with this here. So if we're saying x multiplied by pi over 3, so we're doing the inverse of that to rescale our x-axis. So this pi will multiply by 3 divided by pi. Let's change colour. So that will become a 3. That will become a 6. That will become a 9. We need to go up to 12. So we need to extend that round to 12. Well, and beyond, because we're about to do another shift on this to 15. We've done a shift of pi on it, which is going to be a shift of 3 now that we've rescaled the axis. And we're going to want to do that shift off to the left here. So we're going to want to move everything 3 off to the side, which is the same as moving this axis over to here. So we've got that. Then we need to double everything and shift it all 3 up. So you can see how we're going to end up in the same place when we do that. I think that's just so much more trouble than it's worth. I think it's often the case when you've got these repeating functions, you know, something like a sine function, you know that whatever you've got sitting inside this bracket, it's not changing the fact that we just got this repeating sine wave. So you know what the shape is going to be. We know how to do these two transformations, just plug in numbers. We can see how much quicker it was doing this. You know, you're not getting special marks for trying to go through the ringer of working out 4 different transformations here. So I would say shelve the transformations and just get some key values. As soon as you can find how often it's cycling, you know, how often we're hitting midpoints or troughs or peaks or whatever, then you've got everything you need to know about a sine function. So yeah, I think that's a better approach. So yeah, that's a tough question for 3 marks, I think. But yeah, don't feel as though you're doing a cop-out option just by plugging in some values. I think, you know, you do what works, and I think that works best. Right, pushing on then. The area A is defined as the area to the left of point X within an equilateral triangle with sides of length A. Right, find an expression for A as a function of X when it's on X is less than oh right, okay, so when we're depending on which side of the peak of the triangle we're on. So this is for the first part is when we're on the left of the peak, and the second part is when we're on the right of the peak. So for the first part then, we're going to have that A is going to be equal to, well, we want half base times height. So we've got half of X, that's half of our base, and our height is going to be X tan of the angle. They said it was equilateral, didn't they? Yeah, so multiplied by X tan of 60 degrees. So that is equal to a half X squared times root 3. So root 3 over 2 X squared. Okay, I get a feeling the second one isn't going to be as easy. Now, the second one, I suppose we could do in 2 different ways. If we've got the line, let's draw the line in on the other side. And now we need to add all of this in. So we could say we've got half the triangle plus this trapezium, or we could say we've got the whole triangle minus that bit, which I think is going to be easier doing whole of the triangle minus that bit. So yeah, so let's just say what we're doing: whole triangle minus bit left over. So we need to do that in 2 bits then, right? So the whole triangle is A over 2. Well, it's going to be a half A squared sine 60. Half A squared sine 60 degrees. So that's good. So that is, well, root 3 over 2. So root 3 over 4 A squared. and then we need to take off, well, it's the same, much the same thing again, half the base. So this base is now a minus x, because that's what we've got left for that length. And then the height will be a minus x times tan of 60 degrees. So it's more or less the same calculation that we did here, but we're putting in a minus x instead of x. So that is minus root 3 over 2 a minus x squared. I suppose we could simplify some of it, but I'm not sure I'm really that interested in simplifying that. So yeah, let's just leave it at that. I think that's fine. There's not going to be some amazing thing we're going to condense that down into. And I think we've done a reasonable amount of work there for 5 marks. All right, question 4. Right, we're sticking on more shapes. They're packing these, aren't they? This is no trivial start to this test. Question 4. The figure below shows a rhombus with diagonals A and B. Okay. Contains a circle. Find an expression for the ratio of the area of the circle. So we need the circle divided by the rhombus is what we're looking for here. So the area of the rhombus, right, so we can rearrange these triangles into 2 rectangles, well, 1 big rectangle. You know, if we put one here and one there, then we've got B times A over 2. So AB over 2. So that was a nice bit of rearranging to get that. The area of the circle is, well, let's say it's pi r squared. So that's our r. But then we've got, so what can we say about this r? We're going to have to put in, I think we're going to need a side here as well, aren't we? Because we haven't got an immediate relationship between r, a and b. Okay, let's go with x then as well as being the side. So x squared is a squared over 4 plus b squared over 4. So that's just doing Pythagoras on a quarter of the rhombus. And we're going to have similar triangles in all of this then. So that angle there is the same as that angle there. So that means, yeah, it's going to be, isn't it? Which way round are all these things going to be? So that's the hypotenuse and that's the hypotenuse. Okay, so from similar triangles, we've got the, so A is this length here. So let's compare these. So if we did A over 2 divided by X, because that's dealing with, well, let's say this angle, isn't it? So we're talking about opposite over hypotenuse. So A over 2 divided by X, that's going to be equal to, which is the same as that angle, R divided by half of B. R divided by B over 2, so 2R over B. Right, okay, that took a while to unpick. Maybe I should have drawn those triangles out again to make it a bit easier. But yeah, we've got 2 similar triangles. This one here and any one of these 4 that make up the rhombus. So just rearranging them. I find once I've got one angle in place and drawn a little mark on as what the hypotenuse is, then it makes it a lot easier to see which one's which. Right, so now we can get rid of r's. So we've got r is a times b over 4x. Right, so that now means we can stick this into here and say that we've got pi a squared b squared over 16x squared. X squared, oh, we know is all of this. So that is going to be equal to pi a squared b squared over, well, those 4s are going to take a 4 out of 16. So 4a squared plus b squared. Right, that's good. So now if we do circle divided by rhombus, then we've got all of that and we need to divide by the rhombus. So it's going to get rid of an AB at the top and one of the 2's at the bottom. Pi AB divided by 2a squared plus b squared. Right, that was, again, I think very difficult because there was no obvious path there on what to do. It was a case of, I suppose this happens on quite a few of them. I didn't really know where to go after doing these two bits. So just start writing down things. So that one, it wasn't obvious how that was going to help, but just write it down because you've got some relationship you can bring in. Then start bringing that in. The more things you write down, the more you can start seeing how you can eliminate things. Because we had a problem here with this R. Well, how are we going to get rid of that? Even if we'd gone in and done this, well, we've then replaced one unknown. We need to get rid of one unknown in these two equations. This isn't getting rid of it because it replaces with an R with an X. So we need to do something else to get rid of the X, and that gets rid of the X back into A's and B's. So it's all about adding in more and more equations to try and eliminate the unknowns that we just don't want hanging around. Right, this has been a very difficult start, I think, for the first four questions. I can't think of a PAT paper starting this difficult on any of the previous ones. I mean, this is a whole nother level. So if they keep up at this level, this is going to be some kind of mega epic paper. Hopefully, they're going to start putting some slightly easier ones in. Log ones normally means something slightly easier. Log 5 of 0.7 is equal to 0.7. Find the value of x such that 2 to the power of x equals 10. Okay, right, so we can do, well, we'll log both sides. So we've got x log 2 equals log 10. Well, log 10 is 1. I'm assuming these are all base 10 logs. So log 2 is x log 2. So log 2 is log 10 divided by 5, which is x log 10 minus x log 5. Okay, and that equals 1. So we've got the x 1 minus 0.7 is equal to 1. So x is equal to 1 divided by 0.3, so 10 over 3, which equals to 1 decimal place, 3.3 to 1 decimal place. Right, okay, that wasn't bad. I mean, it's picking up on a different one of the log rules to usual. Normally in the PAT ones, they're getting you to play around with different powers of 2 and 3 and things like that. But not in this one. This was the key part of being able to switch between this log 2 here and making use of this log 5. So yeah, that was a bit of a sneaky one. Otherwise, yeah, it helps. I've seen that sort of thing happen before. So yeah, it certainly helps when you're familiar with it. So keep that one in mind in your box of tricks. Right, now we've got to evaluate this. So it's only going between 1 and 6, so I reckon we just stick in some numbers. So we've got powers of 2 up to 2 to the 6, so that's 2 plus 4 plus 8 plus 16 plus 32 plus 64. So that is 80, 112, 126. And then we've got, what we got on this one? So just going up in those, we've got 2/3. Well, actually, let's do 2/3. It's just going to be 1 plus 2 plus 3 plus 4 plus 5 plus 6, just taking that out. So it's 21 for summing the first 6 numbers. So 14, 26 plus 14 is 140. Right, okay, we're on to some quick ones now. But yeah, when they do those sum ones, and you can see there's only 6 on the top. Well, I mean, it's just so much easier just writing out the numbers and adding them up rather than trying to do anything cunning. All right, looks like we're on a run of, excuse me, a run of quick ones now, because this is just doing a factor thing. Given that that is a factor of it, then find the roots. Okay, so x squared minus x minus 6, so that's one of them. Well, let's factorize what we got on the other bit. So we're going to have an x squared there to make an x to the 4. We'll have to have a minus 6 at the end in order to get a 36. So how are we going to get 24 x's? We've already got 6 x's there, haven't we? So we're going to need 5x. Yeah, because we've got 6 there. We need to take 30 off. Yeah, that's right. So we need to have that 6. That gives us minus 30. That gives us plus 6, which is the 24 that we've got there. Yeah, so that's nice. That equals 0. So let's factorize it all again. X minus 3, x plus 2, x plus 6, x minus 1 equals 0. So we've got x is equal to, well, let's try and put them in order. Minus 6, minus 2, 1, or 3. Right, so it's another quick one. Of course, you can do the long division on all of these factors, but I don't know, I just find it easier talking through it that way. Evaluate the following integrals. Right, here's integral number 1. Oh, this looks like partial fractions. They're only giving us 3 marks though. But it is going to be partial fractions, isn't it? So we've got a over x plus 1 plus b over x minus 1. So we're going to have that a plus b is equal to 1 because that's our x's. And then we've got minus a plus b is equal to 2. So b is going to be equal to 3 over 2. And a is going to be equal to minus a half. Right, so that's good. So that means we're now integrating 2 bits. We've got, let's put the b first because it doesn't have the minus on it. So 3 over 2, 1 over x minus 1 dx. And then it's going to be minus a half of 1 over x plus 1 dx. So that's 3 over 2 log x minus 1 minus a half log x plus 1 plus c. Right, okay. That was quite a lot. And then we've got this one. Right, there's a definite integral this time. So between 0 and 1, let's just write it in a more convenient form. So that's minus a half dx. So that is going to be, well, this one's going to be easier than the last one. So we're just doing that, which means that we're getting 2 root 2 for the first one, and then minus, what have we got, 2. Okay, right, well that 3 marks was a lot quicker than the first one. Given those functions, find the values of x between 0.8 and 1.9, which give the maximum and minimum difference between them. Right, so y1 minus y2 is equal to x cubed minus 4x squared plus 5x then plus 7. Right, so that's our, let's call that D for difference. Actually, let's not call it D because we're going to be doing a D something. So let's call it, I don't know, F for difference. I don't know why. So df dx is what we want to look at here. 3x squared minus 8x plus 5. So we want to set that equal to 0. So df dx equals 0 when, so is that going to factorize 2 things that multiply to 15 and add up to minus 8? So yeah, it will do. So I'm not going to bother splitting the middle term because we've got so many prime numbers. This must be dead easy to factorize. We're going to have a 5 on that one and a 1 on that one, and they both have to be minuses. Right, so we've got that. So we need that x equals 5 over 3 or 1. Are these, they gave us a range, didn't they? Here we go. So they're both inside that range, 1.6 and 1. Well, not 1.6, 1.666, you know. What am I trying to do? Find the values which give the maximum and the minimum difference. I suppose we want to actually know which one is which. So let's do the second derivative. So we've got 6x minus 8. So when x is 1, we've got the negative. So that's going to be our maximum. And just to double check on this one, we're going to have 10 minus 8. That's positive, so that's our minimum. Right, okay, that was quite nice. Relatively straightforward. Slightly weird setup in the question, but once you sort of, get into it, it's just a relatively straightforward calculus question, but not trivial. Given that s is equal to that and t is equal to that, find expressions for x and y in terms of s and t. Right, well, let's eliminate. Actually, that's not going to be that bad. It's just going to be ugly looking things. So we'll rearrange y. We got y is t over 2x. So y squared is t squared over 4x squared. So that means we've got, we're just sticking that into there. So we've got s is x squared plus t squared over 4x squared. Actually, after saying that isn't going to be that bad, that looks horrible. We really need to get that into, I have to get that into x as a subject. Yeah, that's not nice at all. 4s x squared equals 4x to the 4 plus t squared. Yeah, that's horrendous. Okay. Well, I don't really know what else I can do with this at the moment. So we got 4x to the 4 minus 4s x squared plus t squared equals 0. So I think I'll go, do I want to go, I suppose I could complete the square on this. Yeah. Oh, dearie me. No, I don't like that. Really don't like that at all. Yeah, okay. Right, let's put that in. Let's complete as. No, I'm just going to put it in the formula because it's just going to be a mess. The whole blinking thing. I'm going to cop out and put this. So minus b. Let's just stick where we were, keeping that as a 4 and that as a 4. So we'll have 4s plus or minus 16s squared minus, what have we got, 16t squared. Well, at least we get that 4 is going to come out over 8, which is equal to, yeah, we can get rid of a 4 out of there, and there. So that really has trimmed things back. So we've got s plus or minus the square root of s squared minus t squared over 2. That's x squared. So x is going to be equal to plus or minus the square root of s plus or minus the square root of s squared minus t squared over 2. That looks so bad, it makes me wonder if I've done something wrong or taken a really bad method of doing this. But that's an expression for x in terms of s and t. Now we need to get y. So what is y in all of this then? So y is equal to t divided by 2x. You what? So that is going to, well, I suppose we just have to flip that the other way up. Multiply by t over 2. So it's going to be plus or minus t over 2 multiplied by the square root, but now we've got the 2 at the top because we're dividing by it all. S plus or minus the square root of s squared minus t squared. Right, 2 of the ugliest looking answers I think I've ever produced in, or maybe any question. Right, answers on a postcard with that one. I mean, I'm not seeing another way. If you got a better method, then stick it in the comments because I'd love to know something better than that as a way of getting the answer. But there you go. Yeah, horrible looking thing all in all. But hey ho, sometimes you have these sort of things. I mean, in an exam, you just have to take what you can get maybe with the answer. Right, how many of these are there? This is going on for days. Right, this is the last one. At least we finally got a dice question. The numbers shown by 2 dice are labelled D1 and D2. A score is constructed from these by the expression S equals AD1 plus BD2 plus C, where A, B, and C are constants. Determine the values of A, B, and C such that the range of possible values for S covers all integers from 0 to 35 with an equal probability of each one. My word. Right, so we need one answer for each one of them. Right, where to start on this? So we can count up or we can count down. Let's count up on this. So let's say if we had, let's say we had the lowest possible score is going to translate to 0, and the highest possible score is to translate to 35, because we're not changing these A's and D's and C's, A's, B's, and C's. They're constant. So let's assume then that if we get D1 equals D2 equals 1, and let's say that S we're going to make 0, that's our lowest score, is A plus B plus C. If D1 equals D2 equals 6, then that'll be our top score, which will be 6A plus 6B plus C. So we can certainly have all of that. So that would mean that, well, let's multiply. If you multiplied that by 6, you'd get that 0 equals 6A plus 6B plus 6C. So that means that we've got, what's happening here? So C is going to be minus 5C. Yeah, if we combine these, minus 5C is going to be equal to 35. So C is equal to minus 7. I think that looks good, doesn't it? Yeah. Okay, so at least we know what C is. So that leaves us with A plus B is equal to 7. Right, these dice are symmetrical. It doesn't matter which one's which. There's no way we can tell anything apart. So if we had D1 was equal to 1 and D2 was equal to 2, we want that to be our next number up then. Then we'll say that S is equal to 1. So we could say that 1 is equal to A plus 2B minus 7. Yeah, I can go with that. So A plus 2B is equal to 8. So B must be equal to 1. Okay, so then, yeah, so it's like counting up, isn't it? Every time, if B's going up in ones, then we're counting up one at a time on the D2s, which means that A would be 6. So it's doing big, it's like counting in base 6. That's what we're doing, isn't it? So yeah, we go, yeah, it's ticking through. Yeah, because if that went to 2, then all of a sudden the A6 term is going to then jump us up to, I shouldn't have changed that one. You know, if D1 equals 2, D2 equals, well, whatever it is, 1, say, then we're going then up to 12 on there and then counting up one at a time. Yeah, that makes sense. Yeah, so A's are going up at jumps of 6 and B's are then filling in those gaps. So you could have had them the other way round as well. That would certainly work. Or we could have done this the other way round and said, well, actually, the lowest number is at the top and the highest number is at the bottom, in which case we'd have a large positive number for this. C would, well, if it's 7 off the bottom, it would have to be 7 off the top. So you could have had that C is equal to 42. It's going to come out from that same symmetry, which would then make A equal to minus 1 or minus 6, and B equal to minus 6 or minus 1. Yeah, so we've got loads of possible answers here. But yeah, really, we are ticking through. It's like imagining if you've got a number counter where these are counting up from, it's like our tens and our units. This is every time D1 changes, the tens are flicking over. Every time D2 changes, the units are flicking over. So yeah, that's what's really going on, with those. That's another really difficult question. I mean, that's all 11 questions there. that is by far the most difficult PAT section for those first, what have I done now, 7 first math sections for these maths papers, or is it 6 papers. That is by far the most difficult. There were loads of them. I mean, that one was difficult. That one was horrible. That one wasn't entirely obvious. The integrals were fine. That one was really easy. That one was easy. The logs wasn't straightforward, although it wasn't that bad. And the first 4 were, well, 2, 3, and 4 were horrible, and the first one was quite straightforward. So there were only maybe 3 or 4 out of the 11 that were fairly easy. That was a really, really tough bunch. So yeah, if you scored well on that, then congratulations, because that is a mean set of questions. I would imagine that the scores on this particular part would have been much lower than previous years. So interesting that they've stepped it up so much for that, because usually the maths questions aren't that bad. It's the physics questions that are more difficult on the PAT. So it'd be interesting in the next couple of videos when I go through the physics questions, whether they are as difficult, whether they've ramped up the whole paper, or whether it's just the maths part, which has been particularly tough. So, I mean, I haven't looked at the time yet of this recording, but I'd imagine it's longer than any of the other ones that I've done on a PAT paper. So anyway, we'll leave it there and then push on to the next bit in the following videos.